Okay, so continuing our last discussion, now we will look at velocity. So r vector represents the position, and if I want to find velocity, then I have to do derivative of this r vector. This will give me what? This is going to give me the velocity vector. Now let's try to do it. So velocity, we are doing it in Cartesian, is equals to time derivative of, now what is r vector in Cartesian? You know that r vector in Cartesian is x I cap plus y j cap. You know these basis states I cap and j cap, they don't change with time. They are just like for here for reference. The only thing that changes when an object, when the particle moves, is the coordinate. For example, look at point P. If in some time the point P moves here, say to point P dash, then the only thing that has changed are the coordinates. This P dash will have new x dash and it is going to have new y dash. Okay, so time derivative will act only on coordinate because only the coordinates are changing with time. So what will happen here? I'll have dx divided by dt, and this is in the I cap direction, and I'm going to have dy divided by dt in the j cap direction. This is in short written as velocity vector v equals x dot, and this x dot is happening in I cap direction, plus y dot, and this y dot is happening in the j cap direction. Now this kind of expression represents velocity irrespective of the motion. The motion can be anything. For example, the particle can be moving in straight line in this direction, or the particle is moving in this weird curve, or this particle may be moving along this direction. Okay, it can be anything. So let's look at some special cases. Case number 1. If the particle moves, say, in this direction, look at the diagram. If it moves in the r cap direction, okay, then if theta is 45 degree, say its theta is 45 degree for example, then for this graph or for this motion, x is exactly equal to y. Okay, because if you try to draw x equals to y, so if this is x and this is y, then x equals to y represents this line, this straight line. Okay, so if an object is moving, say, along this line, say point P was here, after some time the point P is here, after some time the point P is here, so the point is moving along this straight line, or I can say there is a motion along this line, then what happens to the velocity vector? Both x and y is same, so I can write it as x dot I cap plus x dot again j cap. But this does not mean the motion is happening only in x direction. So you say that, hey, I see only x. Does it mean the object is moving in x direction? No, the object is not moving in x direction. You can see it is moving in this particular direction. The idea is that it is not moving in x direction because I have not removed I and j. Both I and j are present. Case number 2. What happens when y is 0? When y is 0, that is the y coordinate is not changing, it means there would be no term in the velocity with the j cap. There will be only one term, say x dot, and this will be only in the I cap direction. There is no j cap expression. So the absence of j cap expression tells us that now the object is moving only along the x direction. Or say if I draw x here and y here, so point P was here, and according to this expression the point P is moving only along the x axis. With time only the x coordinate is changing, the y coordinate is not changing. Okay, so these are easy stuff, you know this. Our main idea now is to go to the polar way. So in the polar style, what is r vector? In the polar style, the r vector is equal to magnitude of r into r cap. But be clear in mind that r cap contains the information of theta also. So if I now ask you velocity in polar coordinate, then you are going to use this expression. So dr vector divided by dt. Okay, let me write it here. We are looking in polar system. Okay, so what would you get? You'll get two expression. First, the derivative will act on the magnitude r, so I'll have dr divided by dt plus and what is remaining, r cap is remaining, plus next the derivative will work on the r cap, d r cap divided by dt. Okay, this is not looking good, so we are going to make it look good by the following replacements. First is, remember what was r cap? If you remember, r cap was actually cos theta I plus sin theta j. Look at the last lecture, you will understand that this is r cap, cos theta I and sin theta j. So now the question is, oh, we made a mistake, we have to write it cos theta I. Okay, so now the question is, what is the meaning of dr cap divided by dt? So let's do d r cap divided by dt. It's quite simple. First it will act on cos theta, and then, so how will you do d by dt of cos theta? D by dt of cos theta. So you see here theta is a function of time. Why theta is a function of time? Because the point is moving. Look at this diagram. If point P comes to P dash, then if you look at the diagram here, then theta comes to theta dash. Okay, so as the point P is moving, the thetas are also changing with time. So how to do this? This will become minus sine theta, theta dot means d theta by dt. So what is the first expression? The first expression will be minus sine theta, theta dot along which direction? I cap. Similarly, the second one is easy to evaluate. It will become cos theta, theta dot j cap. Okay, now what is this? This is actually equals to theta cap. Theta cap, now let me, so theta cap into theta dot. How? Theta, take theta dot common. If you take theta dot common, then what you are left with? You are left with minus sine theta in I cap direction plus cos theta in the j cap direction. Okay, so In the next video, I will tell how this quantity is theta cap. I'll tell this in the next video. Okay, but now let's simplify this expression. So what we are trying to find, we are trying to find velocity in polar basis states, and the first expression is r dot along r cap direction, and the second expression is magnitude of r into theta dot along theta cap direction. So let's try to understand what do you mean by r dot and what do you mean by r theta dot. So consider point P, which is here, and we know that this is r. So if r is changing only in radial direction, then motion along this direction is represented by velocity r dot along r cap direction. This is the first term. If you look at the second term, so let me represent my point P here. Okay. If you look at the second term, then second term is something you already know. R theta dot is omega. So you already know when we write V is equals to R omega in circular motion. It means this particle P is moving in a circular motion. And if you look closely, there is one more hint that tells us it moves in circular motion, that the motion is happening along theta cap. Theta cap is always perpendicular to r cap. So at any point, the motion is happening along theta cap. So the second term, that is this complete term, represents a motion along the theta cap direction, and the first term represents a motion along the r cap direction. Quite easy. So now in the next video we will look at this thing that we left, which is why this term is theta cap. Okay, so we'll do it next video.